Welcome to Talking Science, where we dive into the latest news from space and science. Professor Gary de Costa from Australia's Arc Centre of Excellence in All-Sky Astrophysics in 3 Dimensions is here to discuss their recent Hypernova discovery. Professor, thanks for beaming into Trekzone.
Thanks. It's always a pleasure to talk about science.
Before we get into it, a quick reminder that you can get behind-the-scenes goss and early access to all Trekzone podcasts by becoming a member today. Click the join button on any Trekzone video, go to the Trekzone/support, put your phone up to the QR code on screen throughout the show. Gary, this hypernova that was out there produced 10 times more energy than a supernova, and it could be the answer to a 13 billion-year-old mystery in our galaxy. Can you tell us more?
Yes, I can. What we've done over the last 5 years is to search for metal poor stars in our galaxy, stars that have abundances that are much less than the abundances in the sun. We do this by taking images with the Sky Mapper telescope at Siding Spring Observatory in Western New South Wales. We follow up the best of those candidates with the 2.3 metre telescope, also at Siding Spring Observatory. And then the very best of those candidates we then observe at telescopes in Chile so we can study their abundances in detail. And we've been doing this program for about 5 years now. And one of the stars that we discovered recently has very unusual abundances. And our analysis for the abundances of this star indicate that, in fact, its progenitor, the star that produced the abundances we observe, must have been a magnetorotational hypernova. So we know it must have been a rotating progenitor because the star we observe has a very high nitrogen abundance. We know that it must have been a hypernova, in other words, a very energetic supernova, because hypernova produced lots of zinc, and we see lots of zinc in the atmosphere of this star. And then finally, we have very high abundances of the elements beyond zinc, the so-called heavier elements, everything from barium, europium, and even to uranium and thorium. And we believe that those are produced in the magnetorotational explosion of the hypernova.
Well, Dr. Brad Tucker and I discussed this in brief on last week's Talk in Science. The hypernova happened just a smidge over 1 billion years after the Big Bang. Now, in universe terms, that's really early. What does this lead you to conclude about another primitive Milky Way star?
Well, basically, in the past, the heavy elements, the ones beyond, say, zinc, have been thought to be produced in neutron star mergers. And you get a neutron star merger by having two massive stars that evolve, that explode as supernovae, leave behind neutron stars as remnants, and eventually those remnants merge and you get a very energetic event. We know that these neutron star mergers occur because we saw in 2017 the gravitational wave signal from the merger of two neutron stars. And at the same time, there was an optical kilonova where people were able to actually study that optical counterpart and in fact see the synthesis of the heavier elements. But it takes time for neutrons, well, for the massive stars to evolve to form neutron stars, and then for the two neutron stars to get together and merge. And so in the very earliest times in the formation of our galaxy, there's actually not enough time for neutron star merger nuclear synthesis to occur. So we need a separate process that in fact produces these elements. And our work, I think, has shown that the production of these elements actually does happen from magnetorotational hypernovae at very early times in the evolution of our galaxy.
So these early stars started the cycle that we've seen repeat around the universe. Once they're done living, they explode and generate hydrogen and helium, usually the simplest elements in the universe, which leads to more stars which live, then die and spread their elements too. But the question has been heavier elements. So early on in the universe timeline, stuff further down the periodic table. I guess the finding that you've led here changes that up a bit.
Yeah, exactly. I mean, I think it's one of the things that people really need to appreciate is that the Big Bang produced hydrogen, helium, and a little bit of lithium. and everything in the periodic table beyond that has been made in stars. The sun's burning hydrogen to helium in its core at the moment. That's how it gets its energy. In a few billion years, it will start burning or fusing helium to carbon. But the sun's not massive enough to really go much beyond burning helium to carbon. Well, massive stars, though, have enough central temperatures that they can produce oxygen, silicon, magnesium, all the way up to iron and the elements in the iron peak. But beyond that, you need a different process to produce the heavy elements. Now, those massive stars explode. They send their productions of their nuclear synthesis into the surrounding interstellar medium, and new stars form from that enriched gas. And so the elements in stars increases as a function of time. And that's how we recognize very old stars, because they have very low abundances of the elements like iron, for example.
Now, is this the first hypernova that we've seen?
No, we do know that hypernovae occur in the local universe. We're not in any sense saying this is the first detection of hypernovae. What we're saying is that we're demonstrating with this star that hypernova can produce the elements, the heavier elements that are difficult to produce from neutron star mergers at early times. So basically we're saying, here's another way of producing these elements like europium, even gold, that happens at early times, and here's some observational evidence that supports that hypothesis.
Now, as you said at the start of today's show, the research all began when the star was identified as metal poor by the Sky Mapper survey out of the Siding Springs Observatory. The European Southern Observatory then picked up the baton and studied it in detail. As you say, as you go down that process through to the Chile telescopes, other members of the research team came from the US, Sweden, Germany, and Italy. How do these sorts of collaborations come about, and what's it like to work with such a diverse team?
Well, it's always good to work with a big team because you get lots of people's input. At the Research School of Astronomy and Astrophysics, we've had a long history of searching for extremely metal poor stars, and so there's expertise here. But we also need expertise in the analysis of the observations. We need expertise in the detailed computation of stellar atmospheres that we use to get the abundances from, and in fact. So the members of the team all bring their individual talents to the group, and as the usual saying, the sum of the whole is bigger than the sum of the individual parts, and that's what actually happens with this team. We all work together very well. And it's these days having international collaborations across the world is just the way. It's just the norm.
It is absolutely incredible and fascinating research as well. Professor, thanks for beaming into Trekzone.
Right, thanks very much. Enjoyed it.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favourite podcast app 5 days a week. Just search for Trekzone and subscribe.